We are currently living in the era of artificial intelligence, defined by massive server farms and algorithms processing trillions of parameters. But the mathematical foundation for these systems actually started on the streets of Chicago during the Second World War. The architecture that makes machine learning possible was theorized by Walter Pitts. In the early 1940s, Pitts was a homeless teenage runaway living under the city's elevated train tracks, completely detached from the formal scientific community. Despite his situation, Pitts spent his days wandering the campus of the University of Chicago. He possessed a staggering intellect for logic and mathematics, eventually catching the attention of theoretical neuroscientist Warren McCulloch. McCulloch invited the teenager off the streets and into his home. Together, they began working on a theoretical model of brain function, based on the idea that human thought could be viewed as pure information. In the 1940s, scientists struggled to explain how biological systems processed physical reality. The prevailing theory, coded memory, suggested the brain worked like a filing cabinet, storing one-to-one photographic images of every stimulus it encountered. Pitts and McCulloch looked directly at the biology of the brain to propose an alternative. They noted that neurons operate in a strict all-or-none capacity. They either fire a signal or they remain dormant. To Pitts, this biological action perfectly mirrored a mathematical principle. An all-or-nothing firing of a neuron maps exactly to the binary digits of 1 and 0. By linking these units together, the physical action of the brain could be translated into mathematical logic. They published these findings in a 1943 paper titled A Logical Calculus of the Ideas Immanent in Nervous Activity. The paper demonstrated that networks of these simple, binary units were capable of performing complex logical operations. Years later, this theoretical math reached psychologist Frank Rosenblatt. Rosenblatt was attempting to understand human perceptual recognition, and he realized that the McCulloch-Pitts paper provided the exact schematic needed to build a physical machine. This 1943 theory provided a bridge between biology and engineering, suggesting that the mechanics of thought could be replicated through calculated code. Rosenblatt faced a distinct engineering challenge, designing a machine that could learn to recognize visual shapes on its own, without being pre-programmed with exact image files to cross-reference. Rosenblatt simulated his initial Perceptron software on an IBM 704, a 5-ton vacuum tube mainframe. Because computers of this size were rare, Rosenblatt ran the first demonstration of artificial machine learning inside the United States Weather Bureau in Washington, D.C. Following that simulation, Rosenblatt's team built dedicated hardware called the Perceptron Mark I. They outfitted it with photoreceptors, tasking the machine to identify handwritten letters. The Mark I worked. Humanity had successfully pulled a theoretical neural network off the pages of a textbook and bolted it into physical reality. This presentation slide from Rosenblatt outlines his radical connectionist model. He rejected the idea of one-to-one pattern matching, arguing instead that information is contained entirely in the connections between neurons. Instead of comparing incoming images to a photograph, a perceptron breaks a stimulus into tiny pieces. When shown the letter A, the machine reads the individual pixels, feeding those inputs into a single layer of artificial neurons. The system guesses the shape. If wrong, it adjusts the weights, strengthening or weakening connections until it produces the correct output. Under the connectionist model, intelligence does not require a hard drive full of files. It derives answers entirely through a web of learned associations. However, the Perceptron Mark I had a structural limitation. Because it operated using only a single layer of neurons, the machine struggled to solve even basic visual logic problems reliably. These errors provided an opening for a competing faction of researchers. Led by Minsky and Papert, the symbolic AI school argued that logic should be hard-coded with specific rules, rather than learned through biological networks. In 1969, Minsky and Papert published a book titled Perceptrons. They used dense mathematical equations to claim the perceptron architecture was a dead end for AI. The publication was highly effective. By 1970, government and institutional funding for neural networks completely evaporated, plunging the field into the first AI winter. There was a significant oversight in the math. Minsky and Papert strictly analyzed the behavior of a single-layer perceptron, ignoring the capabilities of a system using multiple interacting layers. The scientific community abandoned the architecture for artificial intelligence because they judged its potential entirely on the limitations of its first draft. Frank Rosenblatt died in a boating accident in 1971. At the time of his death, he was widely considered the last holdout for a failed technology. He never saw his work vindicated. In the 1980s, a new generation of connectionist researchers returned to the neural network model. They developed the mathematics necessary to successfully train machines equipped with multiple, interconnected hidden layers. Adding these layers solved the exact visual processing failures that had doomed the Mark I, paving the way for today's AI systems. The massive deep learning models currently generating text and images rely on the same McCulloch-Pitts and Rosenblatt architecture from the 1940s and 50s, simply stacked into thousands of dense interacting layers. 80 years ago, a homeless teenager and a psychologist hypothesized that biological thought was actually calculable data traversing a network. If human reasoning is ultimately biological math, how much longer until a layered machine fully outcalculates the human connections that birthed it?